Good day, everyone. I'm Konasandra Balakrishnan from University Malaysia Perlis. I'm going to share my research work entitled Immobilization of Laccase on Magnetized Multiwall Carbon Nanotubes. Lignocellulosic biomass is among the most abundant renewable resources on the earth. It is composed of lignin, hemicellulose, and cellulose. The challenges in the bioconversion of lignocellulosic biomass into useful products start with lignin degradation, as it is a recalcitrant biopolymer. The conventional processing technique for lignin degradation uses concentrated acids and alkalis in order to release the hollow cellulose. However, biological treatment is gaining attention due to its environmentally friendly nature. Different enzymes are required to break down the component of lignocellulosic biomass. Laccase, lignin peroxidase, and manganese peroxidase are three enzymes known for degrading lignin. However, most studies are centered on laccase due to their ability to oxidize phenolic and non-phenolic lignin-related compounds. Xylanase catalyzes the breakdown of hemicellulose to pentose, while cellulase aid the biodegradation of cellulose to glucose. Since enzymatic process exhibit low toxicity, high selectivity, high specification, and the ability to eliminate secondary reaction, in the present study, Laccase was chosen to aid degradation of lignin. To improve the limitations of free Laccase in terms of short shelf life and poor stability, as well to enhance its reusability, immobilization using functionalized magnetized multi-wall carbon nanotubes was carried out. Laccase should catalyze the degradation of lignin into monomers of phenyl propanate. Now let's look at research methodology. The functionalization of pristine multiwall carbon nanotube and synthesis of magnetized multiwall carbon nanotube from functionalized multiwall carbon nanotubes using deionized water were prepared. We have published our work involving synthesis of magnetized multiwall carbon nanotubes using deionized water in the Journal of Chemical Papers. Immobilization of Laccase on magnetized multi-wall carbon nanotube was carried out at 30 degrees Celsius at 200 rpm for 2 hours. The bioconjugates were centrifuged to remove the unbound proteins and dried for 24 hours at room temperature. The binding efficiency of the enzymes on the carrier was calculated using the given equation. The surface topography and elemental analysis of the pristine multiwall carbon nanotube, magnetized multiwall carbon nanotube, and immobilized laccase on magnetized multiwall carbon nanotube were observed using SEM EDX. Figure 4a shows the morphology of pristine multiwall carbon nanotube that portrayed as a tangled tube or snake-like shape structure. Upon synthesis, magnetized multiwall carbon nanotube and immobilization of laccase on magnetized multiwall carbon nanotube, major morphological differences were observed in which irregular shapes or agglomeration structure were detected due to the attachment of iron nanoparticles on magnetized multiwall carbon nanotube surfaces. While with immobilization of laccase on magnetized multiwall carbon nanotube, several bright spots could be observed indicating successful attachment of the enzymes on magnetized multiwall carbon nanotube surfaces. EDX analysis on pristine multiwall carbon nanotubes revealed the presence of carbon with a weight percentage of 98.99% as the primary component in multiwall carbon nanotube synthesis, and oxygen with a weight percentage of 1% corresponds to the carboxylic groups generated due to material purification processing by manufacturer. Addition of iron elements were observed with magnetized multiwall carbon nanotubes, along with decrement in carbon content to 82% and increase in oxygen weight percentage to 7.49% when compared with pristine multiwall carbon nanotubes. The weight percentage of carbon and oxygen in Laccase immobilized magnetized multiwall carbon nanotubes were different than pristine multiwall carbon nanotubes and magnetized multiwall carbon nanotubes due to modifications during immobilizations. Besides, nitrogen was detected evidently due to presence of Laccase. The optimum concentration of laccase immobilized to 0.1 gram of magnetized multiwall carbon nanotubes was determined by varying the enzyme concentration from 2 mg per ml to 10 mg per ml. Based on the immobilization profile, 99% of laccase binding efficiency was obtained using a concentration of 7 mg per ml. Further increment of laccase concentration showed a slight decrement in binding efficiency. The higher enzyme concentration results in excessive enzyme molecules around the carrier, leading to steric hindrance with a lower binding efficiency. Thus, 7 mg per ml Laccase concentration was used for subsequent experiments. Temperature is a significant parameter in influencing enzyme performance by altering its properties. We found the free and immobilized Laccase experience an increment in enzyme activity from 30 degrees Celsius to 40 degrees Celsius. The optimum temperature of free Laccase was achieved at 40 degrees Celsius, whereas the optimum shifted up to 50 degrees Celsius for immobilized Laccase. The shifting in optimum temperature can be correlated with conformational changes and alteration of chemical properties of Laccase due to immobilization on magnetized multiple carbon nanotubes. As the temperature was increased to above 60 degrees Celsius, both free and immobilized Laccase show decline in enzyme activity. Apart from temperature, pH is another common parameter affecting enzyme stability. The relative enzyme activity profiles of free and immobilized Laccase were examined. The optimum pH for both free and immobilized Laccases was pH 5, similar to what was reported in a previous study. And immobilized enzymes offers reusability when compared with free enzymes. The reusability of immobilized Laccase on magnetized multiple carbon nanotubes was investigated using ABTS as a substrate and was noted over 7 cycles. After the fifth cycle, the immobilized Laccase lost more than 50% of their relative activity, parallel with previous findings. It could be due to enzyme detachment from the carrier that negatively affect the performance of the immobilized Laccase. However, this experiment shows the ease of enzyme recycling could be done with immobilization using magnetized multiple carbon nanotube. As a summary, Laccase was successfully immobilized onto magnetized multiple carbon nanotubes via absorption method. The highest binding efficiency of Laccase to magnetized multiple carbon nanotube was recorded at 7 mg per ml with 99% of binding efficiency at 0.1 gram of magnetized multiple carbon nanotubes. The optimal reaction condition of free Laccase was at pH 5, 40 degrees Celsius. Meanwhile, for immobilized Laccase on magnetized multiple carbon nanotube, recorded at pH 5 and 50 degrees Celsius. More than 60% activity of immobilized Laccase on magnetized multiple carbon nanotube could be retained after the fourth cycle of hydrolysis using ABTS. We have published 3 research articles associated with this study. This study was supported by fundamental research grant entitled Lignolytic Kinetics and Thermodynamic Properties of Laccase from Lignin Degrading Microorganisms for Delignification of Agricultural Waste from the Ministry of Higher Education, Malaysia. Thank you for listening.